Hmm. Okay. Okay, let's study diffusion. So the paper I'm trying to read today, before I go to sleep, I'm planning to read 3 papers. Right now it's 2:40. Not sure if I can 3, but I'll try my best. The first paper called Unsupervised Semantic Correspondence Using Stable Diffusion. Let me just lower this volume. So I guess it's using stable diffusion without any learning processes. It's an unsupervised method, and its task is solving the semantic correspondence problem. So let's see. Abstract. Text-to-image diffusion models are now capable of generating images that are often indistinguishable from real images. It means that they're really good at making new images that are really indistinguishable. To generate such images, those models must understand the semantic of the objects they are tasked to generate. So if they want to generate, let's say, a cup, then they must know how a cup should look like. If they want to generate a cat, they should know what to generate. It needs to generate the ears, the eyes, the nose, the furs. It needs to know how to how to generate those. And since it's already good at generating those objects, they are assuming that the model already learned the semantic informations. So in this work, we show that without any training, one can leverage the semantic knowledge within diffusion models to find semantic correspondences. Locations in multiple images that have the same semantic meaning. Hmm. So they're saying that what semantic correspondence is finding the locations in multiple images that have the same semantic meaning. So I have multiple pictures of dogs. In each of those pictures, the dog should have an ear. The model, what it knows is that it knows the locations of each ears precisely, even if, let's say, the image is taken in a very difficult, challenging situation or an environment. So what they're saying is that specifically given an image, we optimize the prompt embeddings of these models for maximum attention on the regions of interest. These optimized embeddings capture semantic information about the location, which can then be transferred to another image. Hmm. By doing so, we obtain results on par with the strongly supervised state-of-the-art on the PF-Willow data set, significantly outperform 20%. That's a lot. And any existing weekly unsupervised on PF-Willow. So what they're doing is, given an image, they optimize the prompt embeddings so that it can have maximum attention on the regions of interest. So I guess, let's say I'm given an image with a cat, like over here bottom. Now I want to locate its, let's say, front paw, which is in this image. And I want to find a text embedding that has the highest attention, and then I want to use that text embedding to the target image. I'm not sure. Let's see. Estimating point correspondences between images is a fundamental problem in computer vision with numerous applications in areas such as image restoration, object recognition, data reconstruction. Work on correspondences can largely be classified into geometric and semantic correspondence search. Geometric correspondence search aims to find that corresponds to the same physical point of the same object that are typically solved with local feature-based and optical flow methods. Semantic correspondence search, on the other hand, the core application of interest in this paper focuses on points that correspond semantically, not necessarily of the same object, but of similar objects of the same related class. For example, given the selected kitten paw in the source image, we would like to automatically identify kitten paws in other target images. So given two images, a source and a target, they both contain a picture of a cat, but the appearance is totally different, and their locations, their formation, it's all different. What they want to locate is the paws of those cats, which is this part and this part. And then you have another target image. So they want to match these points. And yeah, target attention, they are pretty good at it. Okay, so the teaser image, we optimize for the prompt embedding of the diffusion model that activates attention in the region of the paw for the source image, marked in yellow. With this embedding, the attention highlights semantically similar with various target images. We optimize the prompt embedding for diffusion that activates attention reaching the paw. To embed the attention highlights semantically with the target image used to find semantic patterns. So this holds even out for out of district target like a target image style. Hmm, interesting. So semantic knowledge and diffusion models, given an input image and text prompt describing parts of the image, the attention map diffusion models highlight semantically relevant areas of the image superimposed atop the image. So given an input image, if I say paw, the attention myths all differ for paw, collar, shower, and ears. A recent trend to learn is to learn to solve these problems as in many others, computer vision, let's see, COTR. Interesting, you can see later problem. While learning-based methods provide superior informants, these methods can be trained on large supervised data sets, straightforward, fast image, medically is more challenging. We can now simply collect more photos, automatic, human laboring effort. Actually, that is same for geometric correspondence as well. Like even if there's a lot of photos, ground truth labeling those geometric correspondence is pretty much different. In this work, we may not need any ground truth semantic correspondence between independent reference. Neutral and human pre-trained feature, we can use it simply harness the knowledge of the parallel text to image models. They rely on using pre-trained feature is actually the same as utilizing this pre-trained feature in this stable diffusion model. Our key insight is that given that the recent diffusion models can generate photorealistic images from text prompts only, there must be knowledge about semantic correspondence built in with them. For example, for a diffusion model to successfully create an image of a human face, it must know the human face because of two eyes, one nose, and a mouth, as well as their supposed whereabouts. In other words, it must know the semantics of the scene it's generating. Should be able to generate, should be able to choose a whereabouts by product. Note here that your models can also from unsupervised for training. True. Akin to self-supervision, but with more supervision from text-image relationship. Hence, inspired by the recent success of prompt-to-prompt for text-based image editing, we build our method by exploiting the attention maps of latent diffusion models. These maps attend different portions of the image, and as the text prompt is changed, for example, given an image of a cat, if the text prompt is paw, the attention map will highlight the paws with a color. Given arbitrary input image, these attention measure response to mental problem, in other words, we can the problems from the particular location, the diffusion model can be identically symmetric. Note that finding the actual prompt that corresponds to the word is a discrete problem that is difficult to solve. However, these prompts do not have to correspond to actual word as well as the attention map to highlight the correct image locations. So, this is what they're saying. If I say a paw and its attention region is really high in this place, like I can give it another word, a completely different word. Let's say like, I don't know, a word that doesn't even exist, like algomi. And I'll go and I inserted the word algomi, and if it actually gave a better, higher attention in this paw region, I can just use that algomi word instead of the paw. So when it's saying that, finding the best word, natural words in to validate the correct image location. The analogy above holds when we operate on the continuous emitting space of prompt within the core insight. This key in theory approach to find these localized embedded textual inversion. Okay, I need to know what textual inversion is. Given a source image and a query location, you should find random optimize. Like if they're not training, how are they optimizing? We've optimized randomly, and those styles made effective fix. So with instability and randomness of text version, you find multiple. When you find multiple embeddings that have random isolation. We emphasize that our method does not require broad training that is supposed to many points. Means that off-the-shelf diffusion model without fine-tuning. So they're using a diffusion model. What's called LDM. Random crops. Outperform. Okay, so because we're catching up. Ooh, getting I get sleepy. Okay, let's see your later word diffusion. Nutrition, quality samples. Steel tissue made the popular choice, thanks to its lightweight and open source nature. So treat these models. Version. Control this. Repurposing the model for completely new purpose. Prompt to prompt, pseudo segmentation. This is a proper like new features we can use semantic segmentation. Features. Maps. Okay. Method. Semantic correspondence between pairs by literature map given a pair of images respectively served in target, query query. While classical diffusion models for example directly employ the diffusion models to operate on encoded images rather than being interested in generated use attention measured by byproduct. Ooh. Rather than being interested in the generator, we use attention maps generated as a byproduct of this process are present all two stages. In figure 3, the first optimization is to find an embedding that represents the of the query. Attentive team and second information the embeddings from the source image are kept fixed and attention maps for computed, the location, attaining the highest value of attention generated network correspondence. We start by reviewing the basic. Preliminary diffusion models are a class of generated models that approximate the data distribution with denoising base. Yes. Yes, generations. Given T and the noisy image. And noise for that information. The additional treat is given by. They don't operate on each other. Noise case to allow it to Z, to Z, to cut another way to long for me Y. Collaborating embedding the text encoder to the noiser. Okay, method. Given a source image and a query point. Given a source image, query point, we optimize the embeddings. Given a source image and a query point, we optimize the embeddings so that attention map for the data we can step at. Given a source image and a query point, this is a source image and a query point. We optimize the embedding so that the attention map for the data we step at the source image. So given a source image, give a source image, and for a text image, what I want is I want to find a text image. What are these two arrows? During inference, we put the target image in, we use the embeddings with the same denoting depth t, determining the corresponding point in the target as argmax. Mapping images. See. Targeted mapping image definition, which gets frozen throughout the entire process. Okay, go to VE0 diffuse denoise. Get the source attention maps. I don't know what this diffuse is. Let's see what diffuse means. In what we follow, we detail how to compute attention mass given an enclosure and embedding period optimized for embedding that activity as a separate source man how to employ to optimize it for attention mass given an image I. Let ZT be its latent precision. Okay. For the compute query. Tokens. Different. Optimized. Given the source image I and a pixel location. So do you train the model? It seems like they are training the text embed. Okay, second paper is latent space disentanglement and diffusion transformers enables precise earshot and semantic editing. Latent space disentanglement, I think it's talking about stable diffusion. No, DITs have recently achieved a remarkable success in text-guided image generation. In image editing, DITs project text and image inputs to a joint latent space from which they decode and synthesize new images. However, it remains largely unexplored how multimodal information collectively forms this joint space and how they guide the semantics of synthesized images. In this paper, we investigate the latent space of DIT models and uncover two key properties. First, it's inherently semantically disentangled, with the different semantic attributes can be controlled getting different directions. Second, consistent semantic editing requires utilizing the entire joint latent space, as neither encoded image nor text alone contains semantic information. What Heller is saying, we show that these editing directions can be obtained entirely from the text prompt, enabling precise semantic control. Based on these insights, we process and encode immediately remove residual fine image editing. We first encode both given the immune response to the image to accumulate an embedding using a VAE maybe, then using a proposed Hessian score to method we identified and directly. These directions are guided by text prompts. There's a new metric to quantify this entanglement. To achieving controllability is a property of semantic disentanglement, with the semantic actor encoded into distinct subspace identity. Key to achieving controllability is a property of in other words, we can precisely manipulate a semantic attribute affecting the others. Ooh. Why am I later there? I'm just get my jacket. It's kind of getting cold. My jacket. Damn, it'd be nice if I got a cup of coffee right now. Diffusion models have achieved. Ooh, stable diffusion, I guess. Okay, to achieving controllability. Semantic attribute. Unit-based models align text embedding with image via across attention layers. Unit-based diffusion models, text a photo of text conditioner. Diffusion transforms text a photo. Ooh, damn. Sounds good, man. by modifying the image semantics in the joint latent space interaction with text probes. 뭔가를 기억하고 텍스트 프롬프트 디스인테그를 할 수 있다는 장점이 어떻게 생길 수 있을까? Given an input image target semantic. 신기하다. 아, 너무 좋은데? 의 가치로.